set of like key elements, like something like that, only the elements. Okay. And where it is like I'm not caring about any further way how the data is being stored. This is what I mean by the set of key elements. Okay. And output will be, if the key elements are found, then it will return the index of the key element. Mostly we have seen that. Okay. Or if it is not found, it will be just mentioning or returning a -1 or something, or just displays a message that no, the item is not found. And the very well known classical algorithms, or in classical logic, the search algorithms we have are linear search, and mostly we all know that are binary search. What is the concept of linear search? It is, we will be given an array, kind of that, or some list where we will be having elements. You can see like 5, 8, 1, 2, 13, like that. And I is the index value that we have. Okay, so we are starting with a 0 because by default we believe that the array index starts with a 0. So we will be starting with a 0 and we will go till the index value n minus 1, where n is the total number of elements in the list. So for example, for n equal to 8 elements, it will be a 0 to 7. For 10, it will be 0 to 9. Likewise. And say the value or the item that I want to search is equals to 10. So how it will work is simple logic. It will just start with array index 0. Then how to access this element? With this symbol arr of I or a of I, whatever you say. Arr is the name of the array or array name. Okay, so array name is a, then I, and we are checking whether that is equals to 10 or not. Or alternatively, in a pointer notation, it can also be written in this way, right? Because arr by default is the address of the base address of the array. If this is like 100, say for example, then arr will be 100, and I is actually incrementing thing. So since like integers, it's an integer array, so by default the size of each integer will be 2 bytes. So the next element will be like arr plus 1 will be actually 100 plus 2 into the number of elements or the shift I want, that is 1, that is 102. 2 is the size of the integer. So these are like two possible ways. Either we can map directly like this, which equivalently will be understood by the computer in this way. So this basically is your star ARR plus 4. If we want to use a pointer arithmetic. So this is how it will work. Now, whenever it will be equal to is the comparison operator. Whenever it will be equals to the number of items we want to search. If it is found, it will return a true with the I value 7. If it is not found, it will return a false. Simple ones. Next one is the binary search algorithm. Okay, let me also just discuss a little bit of that. Now, for example, say this is the array that we have, and the element that I want to search is 4. Okay. Now, you can understand that if the way of accessing the array is like this, then after we traverse the entire array, the whole array is completed, and we are at the end position. Like 6 is also being completed, and if it is like matching the number of index value as n minus 1, so at least n number of those iterations we have to make to decide that whether 4 is there in the array or not. So in worst case scenario, let me just write down, in worst case scenario, or even in average case scenario, my time complexity, which here is dependent on what? Dependent on the number of searches required till I can decide something. So that is not equals to, let me just cross it, forget about it, like this is that symbol, belongs to big O of, this is the order or magnitude of the number of items present in the list. Because in worst case it is 4, or even in average case it is the best case plus worst case divided by 2 here, because every element here is equally like equiprobable to be accessed. That's why it will be a half best case plus half worst case, and in that case it will be like n plus 1 by 2, but again n plus 1 by 2 is nothing but order of n, because n by 2 is just half, that is a constant, into n. Okay. So this is the average case and the best case scenario in case of linear search algorithm. Now, what about the little advanced algorithm that we have in classical for searching? That is the binary search algorithm. Now, here there is a twist. We all say that binary search algorithm takes a order of log n amount of time. It's not n, it's right now logarithm of n. Meaning earlier, if some element access would have taken 64 units of time, right now it will be taking what? Log of 64. That is only 6. Because here everything is base, or the that value is the 2 only. Okay, that is why it is a log 64 base 2, or it is like only 6 searches are required. But that is not fully true. That is only true if the array itself is sorted. Remember, binary search only gives us the best result so far for searching, which is order of log n, unless we are like using any hashing or something, some other. We are assuming that we are not working on the space, no parallel, anything we are doing. Simple one, simple CPU we have. So in those cases, the best algorithm for searching that we have is binary search that takes order of log n amount of time. But there is a loophole over there. That is, it will only work if the array is sorted. And now how it will work is, just consider here, you can see there is a sorted array, right? It's a sorted one, meaning it's like in an order, increasing or decreasing. The option here is, the way it works is, first I will be picking up the middle element. How to do that? This is say low index, like index is equals to low, let me just write, and this is index equals to high with certain value, where high will be of course n minus 1, and initially my low will be 0, because it is also an array structure. So how to get the middle position? I will be just making a mid equals to my low plus high divided by 2. You can take it either way, either a seal or a floor. Let me just take floor over here. Accordingly it will be adjusted, and if it is exactly like equal, there is no point or any of the further values after decimal, then it's okay. So in that way we'll be getting my mid. So what is here mid? My mid element is 21. Now once I'm getting 21, I'll be putting it in the root, right? So I'm breaking my array from middle. That is why it is an interval search algorithm. Whenever I'm getting at 21, now my base next target is, what is the search element that I want to find? Okay, now say for example I want to find 13. 13 is my search element. Then what I will do is, I'll be definitely knowing that from middle position to high, there is no possibility of getting my 13 number, because why? 13 is less than 21. Once I get that, I will simply discard this entire portion of the array. It's not needed. Right now my array size will be reduced to only this 5 to 19. Why not 21? Because first I'm checking whether 13 is equals to 21 or not. Whenever it is not, then I'm checking whether 13 is less than or greater than 21. Whenever I'm getting that 13 is less than 21, then my entire n element array will be divided by 2. So it will be n by 2. Likewise, my n will be n by 2. Similarly, it will next will be n by 4, n by 8, and likewise till I reach 1. And if you notice, it is a log series pattern, logarithmic series. So my search space here in terms of a logarithm, it works in that way. So this entire binary search algorithm is going to take what time? It's going to take an order of log n amount of time for binary search. But the twist here is, again, getting back over there, that my array has to be sorted. Then only I'm going to get this benefit. If it is not sorted, then what we can do? We can of course use the best sorting algorithm again to first sort the array, then apply my binary search. Now, asymptotic lower bound, meaning nothing can be less than that. Okay, the asymptotic lower bound theory says, theory of complexity, classical complexity says that For searching, sorry, for sorting, the best one that we can get is omega. Omega is for the lower bound, the best case, say for example. So the best first algorithm that we can have, that is the best algorithm that can handle the worst case for a sorted array, for a sorting operation, can be only n log n. There can be no improvement over there. We cannot make any improvement. Heap sort, mud sort, quick sort, in average case, they actually provide us this n log n time. Again, that like bucket sort or some other advanced form of sorting where we are playing with the space, I'm not considering any auxiliary space over there. It's a normal case, then it will be time bounded by n log n. So first, that means for an like unsorted array, what do we have to do? For an unsorted array, first use the base sorting, then I will be using the binary search. So this is my omega of n log n, and this is my big O of n. So it will be like omega of only my n log n, because this is the leading term over here. N log n is more than n. Of course, you can understand log n is something which is greater than 0, so it's a positive term. So whatever we do, it will be actually more than n. Okay, because log 2 base 2 is 1, and log 1, that is not doable over there, and negative we cannot go, so there is no chances of getting fraction if it is like n log n where base is 2. So this is the time complexity of binary search for an unstructured or an unsorted array. Okay, a quick comparison between what we just learned. So linear search is any random order that we can go with. Binary search is when we are having a sorted ones. Size preferred for small list because of the complexity that we have. But if like array size is very big and it is sorted, then it's of course preferable or advantageous to use the binary search. Speed is of course low. This is fast comparing, considering it is sorted. Input data set dimension, multi-dimensional array can also be used because they can be equivalently translated into single dimensions, right? A 2D array can be converted to a 1D array, and that is how the index, either the row measure or the column measure way that works. Binary search, it can be only useful for a single dimensional array. Time complexity is order of n, and here the time complexity is order of log. Till this part, my classical things end. Now, the next column that you can see is for the quantum search. Why we need it? Do we really need quantum search algorithms? Because in quantum, everything is very, very costly and everything is very difficult to implement or to devise an algorithm. Okay, so why at all we need that if we are having like log n complexity or n complexity? Because they are directly not exponential. It is not like 2 to the power n or k to the power n or a very np hard problem. Such problem is not an np hard problem, but still we are using quantum search. The real advantage is it is kind of a mixture between linear search and binary search. It can give us that essence, and searching database and all search operation is the most widely used operation. So even if you just remember the select star from some database, this operation comes a lot more times. The select query comes a lot more times in dbms than the data manipulation or all those kind of insert, update, delete, and of course creation is very kind of less. I'm not getting into that, but most widely used operations are select operations, and they are most even more widely used than insert, update, delete. And right now in the era of big data, AI, gen AI, all this stuff, okay, where we are dealing with a lot of data, so if we can reduce our search time in any form, then or then there will be a huge cost cutting that we can achieve. That was the motivation behind working on the quantum one, if it is able to produce some better result than the classical search algorithm. And yes, we came up with that. It can work on any random order just like linear search. It is also preferred for very large list, unlike linear search. Slow, fast, and fastest. Yes, it is fastest among the three, considering I'm working on the unsorted database. And next is multidimensional data. Okay, this is not possible for quantum because here itself the data encoding is in a different way. We'll look into that. And then comes the time complexity. If you clearly notice, there is only root over of n number of searches or iterations that we have to make in order to decide that whether that item can be found in an unsorted database or not. So this is the motivation for which we are interested for a quantum version. Because now forget about this one, forget about the linear search because we are working on the unsorted data right now. So the thing is, this maybe right now not appearing to be a very kind of a promising one to you because it's rooted. Let me just tell you. Say for example, I don't remember right now if like in this course I've taught like quantum cryptography or not. We were talking about the symmetric cryptography algorithm or something like that. Or you all know like the AES, Advanced Encryption Standard Algorithm, which is a symmetric key or the shared key algorithm. And for AES 256, and this is itself very secure algorithm. That's why a lot many applications right now are where we cannot use symmetric unless those cases we are actually using the symmetric versions. So in this particular algorithm, where there is a lot of quantum, a lot of classical rounds of mathematical operations, mixing, rotating, shifting, we are trying to make it as much secure as possible. So a attacker or a hacker, if they want to hack some cryptographic algorithm which is deploying AES 256, then earlier quantum, they actually needed all combinations checking. The key strength in classical AES was very strong. So these many operations, number of brute forces or brute force attacks, they have to make. But if it is quantum, or whenever quantum came with an attacker, if an attacker has a quantum computer, then deploying the quantum search algorithm, this 2 to the power 256, which was order of n itself, right now is going to take root over of 2 to the power 256, number of combinations checking. And this is nothing but 2 to the power 256 whole to the power half. So this is 2 to the power 128. And in order to achieve this, the logical or the algorithmic qubit, once we have a little more error corrected quantum bits, it is only going to take 120 qubit quantum computer. And you can imagine that the time we achieve like 128 qubit quantum computer is definitely much, much, much earlier than when we can achieve a 256 qubit quantum computer. So this is really a fantastic capability of quantum that we can showcase or demonstrate using a quantum search algorithm. So for this, because maybe it is not breaking the kind of classical cryptography right now, but it's definitely weakening the classical cryptography. Now, the one who was behind this milestone kind of thing was Love Grover. He's also someone from MIT, MIT Mathematics Lab. So he devised this Grover's algorithm in 1996. He is also a student of Peter Shor, who was the again another. There is only two milestone algorithms so far. There is no doubt about it. That is the Shor's algorithm and the Grover's algorithm. Shor devised it in 1994, and Grover was his student only, PhD student or something. So he came up with another algorithm which completely is a different computing paradigm in quantum. In 1996, introducing a whole altogether a different concept of amplitude amplification, and in 1996. And these two are the milestone algorithms in quantum so far till now. So in quantum computing, Robert's algorithm, also known as the quantum search algorithm, refers to a quantum algorithm for unstructured search that finds with high probability the unique input to a black box function that produces a particular output value using, meaning simple words, just returning the index. Okay, using only root over of n evaluations of the function. Now this is of course very tricky. There is a quantum function that we have to devise for that, but once we devise that, it is going to take order of root n amount of time, where n is the size of the function's domain, meaning n is the size of the, say, the total number of key elements that we have to search in order to get the uh, get the required desired output. Okay. Okay, this is just same thing. So you can imagine it like a dictionary search or something. We have to search something particularly over there. Mm, this is the overall encoding. So an input to a Grover's algorithm is, suppose we have a function where it is like f of 0, 1, 2, 3, something like that till n. Then it will be mapped to 0 or 1 first, where n is the total number of items and it is equals to 2 to the power n minus 1, where n, small n, is the number of qubits. Okay, let me do one thing. Let me just directly jump over here. Okay, so what I'm talking about is, say or let my capital N is 2 to the power n, so that our input is an kind of, our input is an n qubit data. Okay, and next is, we have an oracle. We have an oracle which defines the needle in the needle, we call it a needle in the haystack. It's a function known as needle in the haystack function, defined over k such that my 0 is less than equals to k is less than equals to 2 to the power n minus 1. And so you can understand k is one of these 0 to some element between 0 to n minus 2 to the power n minus 1. And this f of k will be equals to 0 for all k except for w, considering w, or we can also call it x, whatever. This is my desired item, desired or marked item. This item that I want to search. So except for w, for all the values of k, f of k, which is the needle in the haystack function, will be equal to 0, and the same function will have the value 1 for k equals to w. So for all the other elements in the unstructured list, it will be making the values 0, it will be making their indexes 0 initially, and for only the one, the item that I want to search for, it will be making it 1. Okay. Now, the Grover oracle, for this, the simple Grover oracle will look something like this thing. This is the oracle unitary. That's why u, f of w, they want to search for. That's why I'm just marking it like this. So this is my, there is one input register and one target register. What is input? What is target? Still, I have not defined them. Out, this is just the input, and this is a target. So the input will be ultimately unchanged, no change in that, but definitely they will have some impact on the target, making the target y XOR f of x. So this is my output target. And what is my FW function? Again, let me just define FW for x. X is for all the input. That's why I'm just denoting it like this. So this will be equals to 0 if x is not equals to w. That is my, now you can understand one thing, focus here. That means somehow target is also one of the input. Okay, that's why I'm just writing 0 to the power n minus 1. So I will be searching for w within x itself, right? And my fw of x will make them 0. And for x equals to w, I will try to make it 1. So, and the y, so say if I can make my y as 0 minus 1 by root. I hope you know that we can do that. This is just the, like, I will be starting with 1, how I can do that. So only this part I'm just writing for a quick recap. So I'll be just introducing a NOT gate. I will make my gate 0 to 1. Then I'll be introducing a header mark. So an x and h will make it 0 minus root 1 by. I'm not focusing on the gates now, that you can do, but this is how you have to break it when you will be devising the entire one. But anyway, if I can prepare my y in this way, then the output will be what? It is ultimately minus 1 to the power fwx times x, and this is 0 minus 1 by root. And why this one is right like this? Because my target is nothing but y XOR fx, and if y equal to 0, we all know zeros or anything will be that value itself. So target will be what? Only fw of x. And if y is equals to 1, then 1s or anything will make it, say 1s or x. It will be x bar. Simple Boolean algebra, nothing extra. 1s or a will be ultimately 1 into a bar plus 1 bar into a. 1 bar into a will be 0. So it will be a bar. Similarly here, at that means if y is equals to 1, it will be, my target will be fwx whole bar. So you can write it in this way. Now if second register means 0 minus 1 by root 2 is unaltered, but my first register has a phase dependency plus 1 or minus 1. Okay, phase dependency on fw of x. Okay, and that means if fwx is equals to 1, the sign of first register is flipped. Okay, so output will be something like this. Output will be, again, this thing. This is the first Grover oracle that we are talking about. So this was my case. So that means when fwx is equals to 0 first, then output will be what? X, because minus 1 to the power 0 is 1. So it's x, tensor product, get 0 minus get 1 by root 2. And when fwx is equals to 1, then my output is ultimately the minus, because minus 1 to the power 1 is minus 1. So minus k takes tensor product this thing. So just now, let me here itself give you a quick understanding of what we are like, where we are heading towards. So, say for examples, I have done something, and first, whatever elements I have just encoded them in qubits. Okay, I have encoded them. So, say now my elements are not like 536, something like that. Rather, they are right now represented in a 0000001, something like that form. So just a quick say note, let me write in this way. What we're trying to achieve here is, say I have a 3 qubit system. 3 qubit system. So first I will make it a superposed one. So that will make 1 over root over 8. Then this will be 000 001 010 011 100 101 110 and 111. Now, where we are heading towards the needle in the that function, and my oracle on that is ultimately will make it in a superposed form itself. What it will make it? 1 over root over of 8. That is a magnitude. And then it will be, say, my search item. Say my W is, for example, say 100. That is 4. 4 is the index value that I should be returning as an output. Then it will be, I'm doing nothing, and these are all the X. So this is the input register I was talking about. So the target will be looking like all the other values will be having a positive amplitude except for this one. That means somehow with this quantum oracle, I am able to do something, some way of identification. Maybe it is in superposed. I have not measured anything. But still, in the quantum state itself, somehow I've identified the target ship over the heart, out of the heart. That is why it is a needle in the haystack function, and this is the first step for Grover. Got it? So this is a note. This is what I'm trying to achieve. So this will make it like this. Now formally, let me write this operator. You can do it in this way. Yes, we can do it in this way. So we can define a unitary operator. So UW, which is equals to identity matrix minus 2 KW bra W. This is the outer product form. So that means you can understand that I will also be in a matrix form, identity matrix. Okay, these small observations we have to make. This is the outer product form. Okay, now when UW acts on KW, it will look something like that. UW on KW. So this will be W. I is identity, so it will be W itself. And this will be minus 2. 2 KW bra W will be acting on that. So it will make it something like this. Okay. Now we know this is again the inner product. This is nothing but 1. It's always 1. The inner product of an element with with itself. Let me write inner product of a quantum state with itself is always 1 per orthogonal. So this is W minus 2W. So this is X minus 2X, which is minus W. So my first step is achieved. So how we will do it is, this is the operator that I have defined, only the operator. Now we have to do the entire quantum state for that, where I will be applying this UW operator, which is a unitary operator. For that, we will take yeah, 345. We will take a linear combination of computational basis. Computational basis means everything like 0, 1 for a single qubit system. For a 2 qubit, my computational basis will look like 0, 0, 0, 1, 1, 0, 1, 1. For 3 qubit, it is 0, 0, 0 till 1, 1, 1. Okay, this we call a computational basis. So once we take that, it will be, now say my linear uniform linear combination is something like my S, or the standard state, let me call it, will be 1 by root n into sigma x equals to 0 to n minus 1. My n, capital N, is equals to 2 to the power n always. So you can write either way, 1 by root over of 2 to the power small n, sigma x equals to 0 to 2 to the power n minus 1 as well. You can also write it in that way, times ket x. But this is a collection of all states. So these are all like collection of states, or collection of all states, and this is how I am making it a superposedly or uniformly superposed combination. I'm adding the 1 by root 8 thing, and I am adding a plus with all the bases. Once that is done, now by definition, since kit W is a member of this collection of this same collection of computational bases, that means my WS will be 1 by root. Okay, let me prove it as well. Otherwise, a few of you might not follow up. For example, what I'm trying to say is, so from S, I'll be taking 1. This is what I'm trying to do. Now, for example, say I have a 4 state. So capital N is only 4. That means the number of qubit is 2. So my S will look like 1 by root over of 4. That is half. And I have 4 states. That means 0, 0, 1, 0 and 1, 1. This is my S. What I am trying to say is, if W will be of course one of the elements, like W can be 0, 0, 0, 1, 1, 0 or 1, 1. Say when W is, say 1, 0. Then what will be my W inner product S? So W inner product S will be, half will be as it is. Then it will be like bra W is nothing but what? If it is 1, 0, then it will be like, it is a ket 1, 0, it will be bra 1, 0 then. So it will look like this, 1, 0, and this is already my 0, 0. Right? This is then 0, like 1, 0, 0, 1. This is the inner product versions. And then it is 1, 0, this is also 1, 0, and this is 1, 0, 1, 1. This is the derivation that I'm trying to make for this particular equation. Now this will be what? This is 0. This is cancelled out. This is also 0. This is 0. And this is only 1. So from entirely it will be 0 plus 0 plus 1 plus 0, which is 1. So ultimately it doesn't make any sense to write it again. So it will be half. Half is what? 1 by root n. So no matter how big set of states you have, if you pick up one element from that set and make an inner product, it will always be equals to 1 by root n. Okay, so this is the first unitary operator that we have. Now Grover also had done something after this operator. This is the first operator that we discussed, UW. Now Grover defined another operator called the reflection operator. reflection operator or US. And he defined this US as 2 get S bra S minus I. Okay. Now, and why it is called a reflection operator? Because suppose we let US to work on arbitrary state, any arbitrary quantum state, psi, get psi. Then on application of US, what will happen is psi will be decomposed or psi will be resolved into one component, along the standard state. This along means parallel to this. And another resolved component will be component perpendicular to standard state S. So that means like psi can now be written as psi parallel plus psi perpendicular. And then if US works on one of the resolved components which is psi parallel, okay, that is along S, then the component parallel to S, that is this one itself, will be unchanged. But the sign of the state for perpendicular to S component will change its sign. And why this will happen? Because the outer product of this one will become 0. We'll have a detailed look on this. But in short, before we jump into the geometric interpretation and all, so Grover's operator, after this is we will be defining, then third operator, again there is one operator which is called the Grover rotation operator. So Grover rotation operator is a third operator in Grover's algorithm. This is called Grover's rotation operator, often represented as RG or Grover operator also it is called. Both are same. How this works is, this is Rg and this is equals to, first I will be applying UW on some state, then I will be applying US on some state. What is UW? The first unitary operator. So this is the unitary operator where my task is to flip the or change the sign of the marked state or the state that I want to identify. All the remaining states initially will be having a positive sign, only the marked state will be flipped, it will be face flipped and it will be like minus. Okay. And US is the next operator. So this is the first unitary operator to change the marked item sign. And this is the next operator, which is the reflection operator that I will be doing. Okay. Though that means the third operator itself is a combination of first and second, and then some addition of a sequence of steps that I have to do. So first you do UW, then you do US. And this together is known as the Grover operator. This sequence is known as the Grover operator. Okay. So Now let me just continue on the same one. So RG is nothing but USUW. So when we apply, we have by now we have set up the base. Now it will be more, little more mathematical, little more quantum. So just let me just wrap your mind in that way, and you can give some break, or I think it's 3:54. Let me at least take 6 more minutes, then we can decide on that. So when we apply UW on psi, the component UW on psi, then the component parallel to W is flipped. When I'm applying UW on this, then the component which is parallel to W will be flipped. Why? There's a phase flip, the unitary operator that I'm talking about. Other values will be zero. That's why only the same one where it is aligned with the same standard state. You have seen there only we're getting like 1 by root over of n. So that means only that will be active. All the other three values 0, 0, 0, 1 and 1, 1 was off. It was cancelled out. So that's why only the component which is parallel to W was flipped on application of UW. So and second is when we apply US on psi 1 and say this is psi 1 and say this is component is flipped and it is making it like this. Say UW psi has made it like psi 1. And now we are applying US, this is a second operator on psi 1, because psi right now has been resolved into, or like right now has to take the look of a psi 1 state, which is a new quantum state. So whenever we are applying US on psi 1, it will make the component perpendicular to S as flipped. So that means two kind of things you can see. So one operator, first of all, W and S, these are the main actors. Okay, these are the quantum states. US and UW, these are the two quantum operators which are operating on both the ones simultaneously. Now one is making one state as flipped, which is parallel to that. One is making the SS1 as flipped, which is perpendicular to that, but both are operating, both are working together, right? That is why Grover rotation operator is fully based on the change the phase, then you apply reflection. Change the phase, then reflect. Change the phase and then reflect. This entire step we have to keep on repeating. So it looks like this. So flipped, and it will make it say for example. So this will make it ultimately, the transformation will make it psi 2. So the next time my UW should start with psi 2. Okay, because both the operators I am working in a sequence. Okay, this might look a little complicated, but let me just show you the geometric interpretation. So say, let me just draw it first. So this is the axis, y and x axis. So this is my W first. Then of course this will be component perpendicular to W. Similarly, this is also like component perpendicular to W. Now say parallel to we cannot draw. So say this is my superposed state I'm starting with. W is a mass state that I want to which I want to achieve from the superposed state. That is what my target is. Now say this angle that it is making with the angle or line perpendicular to mass state is theta. And This is the psi state that I'm getting. This is an arbitrary quantum state to start with. So this is one of those X states. Okay. X is the input registered one. I'm picking up one by one each. That's why I'm just marking it as psi. Okay. And the angle made by psi with W or mark state is phi. So of course, this angle then will be, if this is theta, this is a perpendicular. So this is pi by 2 minus theta. This entire angle. And how to break the components? If this is S, this is theta, then this line is for S cos theta. And of course, this line is for S sin theta. Now, firstly, I'm applying UW on psi. UW on psi. Okay. Then where I will hit for this is the component parallel to W will be flipped. So that means it is exactly will make some change, like if this is phi, this is, and I'm applying what? I'm applying the first operation, which is UW on psi. So I will be somewhere like this. This is my psi 1. Okay. So this is due to UW. And if this is phi, of course, this will also be phi. And say the S vector, this S vector component also, let me just draw the both the components. My unitary is done. Now I am heading towards a reflection operator. For that, what will happen first? The component will be divided into the like parallel and this that thing. So that means my S now needs to be divided. So this is S. So parallel to S is this one itself. Let me just draw a line perpendicular to S. So how it will look like? The line which is perpendicular to S will look like this. If you notice, this is something which is perpendicular to S. Let me just draw also the line for this area. So this entire line is perpendicular to S. And let me assume the angle made by this with this is lambda. And the next step, the application of like US on psi 1 will make it the component perpendicular to S as flipped. Okay. So that means something like this I am going to get. And this part will now be also lambda. Same way as we have done like psi, or sorry, phi, likewise only here. So this is my third step. This is the second one. Starting from this, making it here. Then I'm the third one is application of US. So this is due to US. So mark it down. Oh, okay, and if this is S, this is also S. Just like this is WL, this is WL. So this is S, this is S. So this is the entire geometry of all these states and all the operators. So the angle between KW and SL, is perpendicular is your theta, and this is also equals to the angle between Ket S and W perpendicular, right? And this is equals to theta, and if you notice, theta is nothing but it is equals to psi plus lambda. This is observation number 1. Second observation from the geometry we can get is the angle of rotation. The angle of rotation, that is how much is the angle difference, phase difference between my initial psi before I had applied UW and final state, which is psi 2, that will be equals to psi and psi 2. That will be, if you see, it's phi plus this thing, okay? And this one also will be equals to my theta, which is equals to phi plus lambda. So this is nothing but first phi plus this is theta plus this is lambda. So this is phi, this is theta, this is lambda, and this is my initial state, and this is my final one where I have. So this is my side 2 as well. This is WL, okay? Don't get confused with it. So this is my final state, and this is my initial state with which I've started with. So that will be phi plus theta plus lambda. And theta plus lambda together, phi plus lambda together is also theta. So it's ultimately theta plus theta is equals to 2 theta. This is also very, very important observation to make. So that means after one single Grover rotation, the angle or the phase difference between the initial quantum state and the final quantum state is phase shifted by 2 into theta. And what is theta? Theta is the angle, primarily when we started with, theta is the angle made by my superposed state with not W, that is not the mark state, rather the perpendicular of the mark state. Always remember that. Theta is the angle made between superposed state and not the mark state. Superposed and marked, these two are the actors. So theta is not the angle exactly between S and W, it is angle between S and W perpendicular. Okay. So whenever we are doing that calculation, we have to keep it in mind whenever we are trying to get the value of theta, that after that we have to make a 90-degree minus theta to get the angle between that. We will do that. But just remember what theta is the angle between my S and WL. So let me write after only one iteration I have made. Okay, after one successful Grover operator or Grover rotation between initial state and final state, the angle is 2 theta. Okay. Now, say my initial superposed set of states, the S, will contain 100 number of states, out of which 99 are not desirable and one is the ideal state. Sorry. Are you getting it? That means the S is right now 100 states. Only one of them is desirable. So what is my target? What exactly we are trying to do from over here? Our target is how we can convert from S to W, that is from all the 100 states, how we can derive to the most desirable state, which is the one that I want to return. Okay, so the main question of Grover is nothing but how to convert through certain. What is the certain? That is the Grover complexity only. That how many such iterations we need. I will come to the certain point later. So how to converge through certain iterations from S to my W. Okay. For that, how we do it is, let me give you an example. So example is a first arbitrary state psi resolved along W and WL are W perpendicular. Okay, that is like this. Psi perpendicular plus psi parallel, and angle between S and WL, what was? It was theta. And the angle between S and W was what? If it is theta, it was like pi by 2 minus theta. Now say we have a 4 input data. Only 4 input data I am choosing, meaning n equals to 4. The initial angle between S and W. So let me assume that is cos theta bar, or let's say theta bar, not cos theta bar, or it is like theta bar, and then we trying to compute cos theta bar, where theta bar is also like pi by 2 minus theta, and we want to calculate cos theta bar, which is equals to get S into kW divided by the amplitude of that. Okay, so this is nothing but half, and this is nothing but, this is basically root over of like half square plus half square plus half square, something like that, for a 4 input data. So it will be like half square into 4. So if you calculate, it's ultimately only the numerator, which is half. So that means my cos theta bar is half. So theta bar is equals to cos inverse half, which is cos inverse half is nothing but cos 60 degrees half. So this is 60 degree. Therefore my theta will be okay, let me just write, this is theta and this is theta bar. So my theta will be pi by 2 minus 60 degree, that is 30 degree. So a single Grover rotation will make it or shift it by 30 degree. Okay, because it is or sorry, it is a theta, then the single rotation will make it like 2 theta, that is 60 degree. Please assume here we are just taking the S and W angle as theta bar, and finally we are trying to shifting, we are doing with the 2 theta calculation. The theta and theta bar, you can check it also, like what is theta, what is, but just follow the geometric interpretation for that, what angle you are taking. So cos theta bar, we can, how to get that angle, cos theta bar we will be, or cos theta we will be calculating that inverse we will make, and then we will subtract that angle with from 90 degree. Once I have that, I have the theta, but remember one single Grover rotation will rotate it by 2 theta. So after that, I will be multiplying it. So one single Grover rotation for this entire 4 input data set or 4 input states will make the angle change of 60 degree. Now the next question is to focus on the certain word, that how many total such iterations we need. This is the most important, most important question. How many iterations, or how many such Grover rotation, where one Grover rotation itself is divided into so many components, like unitary followed by the reflection. Okay, after all these things, one iteration will be completed. Now how many such iterations we have to make is suitable? Why suitable? Because this can happen. Just see the picture. This can happen that we also like keep on doing it on the same plane, like in the like x and y axis, for us to assume like that. But let us just think it in this way. But we are never actually reaching w. Why? Because maybe we're exiting w again. So s or psi after through s and the w, all the operator ultimately is heading somewhere towards here. Maybe here is my psi 3. Whenever I'm making whenever I'm making another time the Grover rotation operator, that is a unitary, and this one, maybe next time, when though I was very close to w, I might shift again in somewhere in another direction. So it will be an infinite thing, right? So we have to pause somewhere. So there should be a maximum number of rotations possible or suitable that we should be carrying out. More than that is not desirable, because ultimately if that we do, maybe we cannot never converge to the desired state from the superposed state. For that, the next question is this one. So let us try to see it, derive it. Say my psi is sigma x ax times x. What is ax? Probabilistic amplitudes. Okay, and s is nothing but 1 by root n sigma times this thing, x equals to 0 to n minus 1. For the purpose of derivation, I have to take the generic terms. That's why it looks a lot more heavy. But these are like simple ones only. If you just replace the amplitudes with certain values or it with a very small example, like, then we can see that. So this s and psi, the inner product, will make it 1 by root n. This sigma sigma, let me, because both are same, so let me just write x or x bar, whatever you write. Ax then is x into x, so inner product x bar, and this is 1 by root n times ax, x equals to 0 to n minus 1. I'm just writing from whatever I'm getting. I'm just merging both of them, nothing else. Okay, and this has now become 1 because ultimately they are the same one. That's why I'm getting that. Let me just write it as x equals to x bar will make it this, and the remaining value when x is not equal to x bar, it will be simply cancelled out. So these are just some small step jumps that I'm doing. Okay. So if that is the case, now let me calculate the mean amplitude. The mean amplitude. Mean amplitude means average amplitude. Let me just write it as a bar, which is nothing but sigma ax by n. If that is the case, then can we write s and psi, their products will be this was the thing, okay, and a bar is ax by n. So what I'm trying to write is from this, okay, let me show the derivation. This is 1 by root n x, okay. So from this I can write root n by n. This is the value, same value I'm just writing over here. X equals to 0 to n minus 1. I have not only written that. So this I can make like root n by n. Just cut it. Then it will be numerator root n. Sorry, denominator root n. Then this one I can write it like sigma x as it is I'm writing. And root n, if you just take it otherwise, then sigma ax by n, it is nothing but my a bar. So this is nothing but root over of n into a bar. So this is a small step that I am doing. That this product will also, in terms of mean amplitude, will look like root over n into a bar. Okay. So now say U is the my like big operator, the reflection operator that we have, that is applied on this ket psi. So what was the definition of this operator? This was the outer product of A is 2 times of that minus I. Now this will be applied on ket psi. This is the operator, US operator. That means this is nothing but this thing I can write minus I into this one is nothing but this. And this can be written as what we got just root n into A bar minus ket psi. Now this can like S can also be written as 2 root n into A bar. Let me write here. Then S I am writing over here like 1 by root n times this x, and the sigma I'm just writing s in a like with its definition formula 1 by root n this thing into x. If I write it that, then this will be cancelled. So this is this and this is okay. And the psi is also can be written as ax x. This is the one which with it started with. Okay. So this is sigma x, let me first write, then 2a bar, sigma x means for all the values it will happen, 2a bar minus ax times this is another interpretation in terms of the mean amplitude. Again telling there is no way we can skip all these things if you have to understand Grover in full form. So first we have seen the reflection operator, what was like geometric interpretation, what was the purpose, just to showcase that the number of like the phase angle between the one Grover rotation operator will make the angle between the initial and the final state after that single rotation is 2 theta. Only to demonstrate that we actually needed the geometric interpretation. The second one, what we are trying to do is trying to do something with the mean amplitudes. So U is on psi will actually make certain impact like this. Okay. So before application or before US was applied, amplitude was kind of AX for all X. Okay, right? And after this is applied, now the amplitude for all X is 2A bar minus AX. Now if we measure both amplitudes, with respect to mean amplitudes, then this will be the amplitude with respect to mean, or the initial amplitude will be initial amplitude with respect to my mean is nothing but this is the thing that this is ax minus a bar with respect to, that is the deviation or what is the gap that I am taking with respect to that. With respect to 5, this is just a scale, but what is the scale? That is the mean. And the final one on application of this with respect to mean will be with respect to my mean a bar will be say ax was a bar, I'm just writing it in a different way, say ax was a bar plus minus delta. Then 2a bar minus ax, the final one will be something like 2a bar minus, this is what? This is a bar plus minus delta. So this is nothing but, I can write, that is a bar. If I just write it, 2a bar minus a bar is a bar, and this will be minus plus delta. So this is nothing but, we can write it down in this way, that is, it is nothing but minus of, ultimately the reflection will be like this, that is a bar plus minus delta, and this was the earlier one. So it is right now minus ax. From this, and why this is very important, let me just take one example first. Why this is very important, the process that we trying to establish is inversion about the mean, for which we need the mean amplitude interpretation of us, or the reflection operator. Let me just take an example, say n equal to 8 states, and oracle after application of fwx, let me write oracle, what's the time, okay, oracle after application of fwx, that is the first one, the needle in the haystack function, that is over, has already some knowledge of what? Knowledge of the mark state. There is somewhere we are in the middle. Mark state identification by oracle has already been done, and say it is, say that mark state is w, that is equals to 4. So what are the quick notes? That is w is 100, and my s is of course all the states, the superposed one, that is 1 over root over of 8, then 0002, 100 will there, and then it will be 111. These are all the 8 states, and probabilistic amplitudes of each of the state. Let me write amplitudes of each state which is not equals to w, of course, that is my 1 by root over of 8. But w, since I made it like minus, if you notice also earlier we made that interpretation, minus of, or the like phase flipping of one of the marked state. So amplitude of state which is equals to w will be minus 1 by root 8. All these things are after only the first oracle is completed. Now next part is what we are trying to compute, the US operator, or the reflection operator, in the algebraic or the mathematical form, not the geometric one. For that, what we need to do, we need to calculate the mean amplitude. So the mean amplitude will be what? 1 by 8 into all of these ones. 1 by root 8 plus 1 by root 8. Let me just write it. Okay, for this is 0, 1, 2, 3. For 4, it will be minus this 5, 6, and 7. This is the entire thing. If we have to calculate the mean amplitude, and all of the amplitudes divided by 8, so one of the values will be cancelled out. So from here 6 values are there, so it's 1 by 8 into 6 by root 8, which is equivalent to, I think, 3 by 8 root 2, something like that it will be. Okay, so a bar was 3 by 8 root 2 after only uw is done. We have calculated mean, but till now US has not been applied. So till now the situation, if we calculate the mean amplitude, will be 3 over 8 root 2. Now on application of mean, on application of US, sorry. Now on application of US, we'll make it what? we'll make the states as the new amplitude. The new amplitude is what? 2a bar minus ax. That is what we got. So now if we calculate it, so for therefore the new amplitude of all states which is not equals to w, all the other 7 states, for them it will be, if I just calculate, it is ultimately what? Uh, ax is what? Ax is 1 by root 8 and it is 2 into what was my a bar? 3 by 8 root 2. 3 by 8 root over of 2. So this will be ultimately, if you do the calculation, 1 by 4 it will be, then it is 4 root 2. You can also do the addition calculation and all. So it will ultimately be 1 by 4 root over of 2. After you do that. Okay, you can check it, it will be same. Okay, and or even if the exact value are not calculating, then also let me just show you one thing. The new amplitude, why Grover was like really great is he invented it in this way. Once I change the mark state 1, first make it negative, then I will do something. Then something will reflect as the state which is equals to w. It will make it 2 into 3 by 8 root 2. What is the ax for the mean amplitude? Minus 1 by root 8. Initially there is a minus, so it will be minus of minus 1 by root 8. If you calculate it, it will be of course a value which is much greater than that, and the exact value will be 5 by 4 root over of 2. So the entire picture is something like that. Initially we will be starting with all state as equiprobable state. 1 2 3 4 5 6 7 8, all of them are equiprobable. So this is the probabilities of all. Probability of all of them will be 1 by 8 and amplitude of all of them will be 1 by root 8. Simple one. UW, then I will be applying. It will make what? It is 0, 1, 2, 3, 4, 5, 6 and 7. Then I will make what? I will don't do anything with the amplitudes. I will simply changing its phase here. I will make it here. So here it will only be minus 1 by root 8. All the other values are plus 1 by root 8. 5, 6, 7 are as it is. And then US, it will do a simple one. Calculate the mean, twice it. Then you subtract the actual amplitude. And again, because of the beauty of quantum superposition, if I just apply this operator for once, it can be parallelly applied on all the operators or all the states. That is the beauty of quantum superposition or parallelism. Next, what will happen is, initially it was 1 by root 8. Right now it will become even lesser than that. And it will be all the other values, though they are positive, their amplitudes will be less. And this one which was here, I am just with a simple math trick, I am just changing again the phase to positive, making it plus 5 by 4 root 2, and it will be like this. And then the remaining ones will be as it is. So this is 0, 1, this is 2, this is 3. Right now this is my 4. This is 5, this is 6, this is 7. And this is only after one Grover rotation operator. Here the number of states are very little. That's why you can see a 5 times increase in amplitude. Okay. Whenever the number of states are a lot more, maybe this will not be exactly likewise, or even if it is, while we measure it through a quantum measurement circuit, we might not get this much of a like positive result. For that, we need to do these entire things, repetitions, again and again, so that we can get the desired result. But the process, the entire process that I have shown to you, where the marked state ultimately will be getting a lot more amplitude, resulting in an increased probability, because amplitude square is the probability, and ultimately in Qiskit the probability will be reflecting. So the entire process, this entire process is known as inversion about the mean, or inversion about the mean. And with this technique, so phase shift or unitary phase shift plus the inversion about the mean, these two concepts together formulated the best paradigm, not the algorithm, for a lot of quantum algorithms, not only Grover. And this technique is known as the paradigm, like quantum computing paradigm that has evolved is known as QAA, or quantum amplitude amplification. And this gives us that essence that even in a superposed state, without doing anything, any breaking of the quantumness, we actually can increase out of the superposition only the amplitudes of our desired states. Okay. Now, this till now, whatever we have seen is all about, all is the reflection of one Grover, but still we are left out with that thing that how many total those number of iterations are required. Let me just devise it right now quickly. Say I need m number of iterations to bridge the gap. Why bridge the gap? That is our desirable thing, that we want to converge to the marked state from the superposed state. So to bridge the gap between my S and W, which was what? The angle between S and W was not, as per the geometric interpretation, it was pi by 2 minus theta. Now say I need m number of iterations to finally exactly equally match the angle and the iteration into one iteration making what angle. Okay, so what I mean is simply one iteration will make 2 theta. I will be making m such iterations. That means m into 2 theta. This should exactly match with pi by 2 minus theta. So if you calculate the value of m, it will be like 1 by 2 theta into this thing, which is pi minus 2 theta by 2. So this is pi by 4 into 1 by theta minus half. Okay, and what is 1 by theta? Okay, this is pi by 4, this is this one. So from this, what we know is, now let me just try to get the value of theta. Okay, now we know sine theta, it will be equals to 1 over root over of n. And if theta is very small, then my sine theta can be expanded as theta minus factorial plus this thing and all. So this is, again, this is what I am getting is everything from that geometrical form itself, cos theta and sine theta, from that value. So again, from this thing, just take the component, then you take the inner product or the outer product, do that simplification, you will be getting this value. So once that is done, now theta, if theta is very small, then the series of sine theta will ultimately, ignoring the higher order term, we can make it like only theta. Okay, because whatever is the theta, theta cube by this and all, they will be even much higher than that. So considering that, so ignoring the higher order terms, so it will be something like that. So that means my theta is nothing but, if sine theta is 1 by root n, then I can simply ignore the sine part and I can write that theta is also equals to or equivalently equal to 1 by root n. So if I replace it, it will be pi by 4 into, now if theta is 1 by root n or equivalent to 1 by root n, then 1 by theta will be simply root n minus half. So I'm getting the m as pi by 4 into root n minus half. So this is a constant term. This is 45 degree. This is half, another constant. So from this I can write m belongs to order of only this term, which is root n. And what was my m? The number of optimal number of iterations required to match the gap between S and W. Therefore, we can make that the optimal number of iterations needed to also at maximum, we don't need more than that. That is a benefit that we can get, and we shouldn't be exceeding that. That will also be disadvantageous because we will skip the desired one and again keep on looping in the infinite way in that particular geometric form. Okay, so the optimal number of iterations needed to converge a successful grover, or say grover, where it converges, is root over of or order of root over of n number of iterations. Okay, there is one more derivation and one more form. I want to tell you the form first. I'm skipping it. You can check it. There is also a relation that we can establish. Again, these are all the like theorems. Okay, these are the extended version. The primary versions is over. Like two more extension I want to talk about. That is the relation between, and try to prove it. The relation between theta and n. Theta and n. I was talking about choosing a small theta and n. So that means theta also can have a kind of an effect on the number of iterations. So the relation between theta and n is nothing but sine 2m plus 1 into theta. M is the number of iterations, total number of iterations now, theta, that is equals to 1 minus 1 by 2n. This can also be proved, but right now ignoring it, you can check it by your own terms. Okay. One more interpretation also that Grover made is the matrix form of interpretation using a diffusion matrix form of interpretation of Grover. That is, since it is matrix, it will be a row and a column. So I and j I'm taking. How to fill up the matrix is dij, the values itself will be minus 1 plus 2 by n, where I equals to j. That is for the diagonal elements. And for other cases, it will be simply 2 by n if I is not equals to j. And the diffusion matrix D dij was the elements, were the elements. So d will look like minus I plus 2j by n. Again, what is j? Let me write. So I is the identity matrix here. Identity matrix. This is called diffusion operator. Let me write. So I is your identity matrix. So diffusion operator itself is also a matrix. So this is also diffusion matrix. And this J is a n cross n matrix where each element is 1. Each element is 1. All 1, 1, 1, 1. For a 4 cross 4, it is all 1. Kind of that. And J by N, this thing together also significantly reflects the concept of projection operator. What is the meaning of projection operator? That is J by N whole square is equals to J by N. Okay. So D matrix, so diffusion matrix, whenever it will be applied on say some amplitudes A1, A2, likewise an, where n is the total number of states starting from 1, this will be minus I plus 2j by n into a1 a2 till an. So this thing also will show what this will also mean. That is a fantastic thing. If also this is an operator, that combined way will reflect the effect of the inversion about the mean operator or the reflection operator, and it will also make it like this is also it will make it like 2a bar minus a1, 2a bar minus a2, likewise 2a bar minus an times this will be applied on a1, a2, an. And how it will make the change is say let me take a one example, say n equals to 4, small one. So j by n is j by 4. Okay, that is j times, I can just make it over here 1 by 4, a2 by 4, a3 by 4, and a4 by 4. What is j? A n cross n matrix where all elements 1. So here it will be 4 cross 1 by 4 cross 4 matrix, and here it is all 4. And a 4 by 4. If you multiply them, what it will be? 1 into a1 by 4 plus 1 into a2 by 4, 1 into a3 by 4 plus 1 into a4 by 4. So it's kind of a1 plus a2 plus a3 plus a4 by 4. Similarly, the second one also same. 1 into a1 by 4. Similarly, here as well. Right? And what is this thing? This is nothing but the mean amplitude of a1 till a4. So we can write it down as what I'm trying to do, j by n. Okay, so j by n is giving me what? A bar, a bar, a bar, and a bar, where a bar is nothing but a1 plus a2 plus a3 plus a4 by 4, mean amplitude of all the amplitudes. Then 2j by n, 2j by 4 will be what? 2 times this thing. Let me go back. 2j by n we already computed. Now it is a minus I, right? So I is what? Considering I is 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. So this is minus I. So minus I will be this thing. Now minus I plus 2j by n will be what? You have to add both of them. This one and this one. Sorry, this one and this one. Okay. So it will be what? It will be 2a bar minus, and this will be applied on what? A1, A2, A3, A4. Okay. So this is minus 1 plus 2a bar. Okay, I'm doing what? Here I'm directly just writing it with the diffusion matrix, whatever I have. Okay. That's what I have over here. A1, A2, A3, A4, all those things. So the diffusion matrix we are getting here, this is D. Okay. I can again do that. This will be something like that. So if I just merge them together, if I just merge them together, it will be, that is D on psi. I'm just merging the diffusion operator right now with psi. It will be 2a bar minus ax, the entire thing on application of x and with a sigma x. That was my psi. And minus I plus 2j by 4 ultimately. This one, the operator, it will give me 2a bar minus a1, 2a bar minus a2, 2a bar minus a3, and 2a bar minus a4. Okay. And this diffusion operator, that's why also represented as WRW, right? This R is the selective phase rotation. This is not the Grover R. Okay. This is the selective phase rotation. And this is the W is the Walsh Hadamard transformation. Transformation matrix. And this one also like same. Okay. And the circuit for entire Grover will look something like this. Well, starting with 0. Then we will be applying the Hadamard. Again, this can be a little abstract circuit, meaning a lot many gate decomposition might not be there. That will be the implementation specific one. So this is your input register. This is the target register I was talking about. So this is 0 minus 1 by root over of 2. So this will likewise will be fed to a Grover oracle along with the target register. Is this one. Then again you keep on applying them through a diffusion and so on. This will go on. At the end it will be again like this. Okay. Everything the target register after 1 will be reflecting. So this is how you do. Keep on doing it. And this is the same thing that you have to repeat for order of root over of n number of times. So this is overall, say, kind of an initial picture of Grover. Okay. So there are a few slides. Okay. Let me just quickly go through them. Okay. This is what exactly we have looked exactly. Maybe the way it is written is a little more different. They're the same thing. Okay. This is a picture of amplitude amplification. You can see that. So these are the encoding. These are way more mathematical than what you can see exactly in this slide than what I have shown. That's why I have separately like shown it to you. But these are overall might be useful for all of you. So somewhere like it, you can see like W is a marked item that you can see in the deep purple shade. Okay, we're starting with that. What I was trying to show is also, yes, we can see after root over of this is less than equals to 1 by root n iterations. Actually, this is not exactly 1 by root n here. It shouldn't be present. Just ignore that here. Rather, here you can say after we are actually measuring it, it will somewhere look like this. Okay. Take only the concepts from here and all the mathematics from what I have written. Okay. Initialization, phase inversion, and amplitude amplification. And amplitude phase inversion and amplitude amplification together, you have to repeat for root over of n time. Okay. And after that, of course, you have to make a measurement. Again, this is another high level circuit for Grover search. The algorithm: simply make the superposed state, then perform Grover iteration root n number of times, where in each iteration you have to first apply the phase oracle to change the phase of the mark state. After that, you have to apply the this thing. So this is the entire thing that I am doing. So you can see here we are just making two. What I have shown it for one. This is how it will be encoded through several, like these are the stages. These are again the very like minute level or low level decomposition of the gates that has been shown here. This is a control Z gate. Okay. CCZ. Okay. Mm, and the same thing. So somewhere like this kind of an output you should be watching. For the ones where I should be getting some output, though the other outputs also should be there, but they are very minimal. So they are almost like negligible. But they will also be present with different outputs. But those will be minimum. So likewise, you are going to see something. Give the number of inputs, give the keys to search, then it will give you the number of rounds needed, like one. This is the iterations. Rounds is also equivalently you can refer as iterations. Let me quickly skip it. Yes, so application of Grover is one application is anywhere that you actually want to deploy some search operation. Maybe like 3 search can be one example. And also I want to talk about the kind of speed up that it is giving. When we were like discussing the AES one today, for the complexity of Grover, so n is right now root over of n, and linear search is, I'm ignoring binary search because that is for the only the sorted data. So linear search is n. So from n I'm getting rooted. What is kind of this speed up? It will be called. It's also a quantum speed up called as a quantum advantage. But again, we cannot call it a supremacy. Supremacy term is specifically associated with something where we can show some demonstrable exponential speed up, which is there in the shorts case. But some improvement it is showing, which is a quite a good improvement. It is also like showing what kind of a speed up. It is a quadratic speed up. N to root n is a quadratic speed up. We have a paper together known as a MNDS algorithm. You can search it over internet as well. It is for the quantum version of the ant colony optimization, where we actually use this part of the Grover subroutine, which is amplitude amplification. So we actually used a tweaked version of Grover, and that is the benefit of this paradigm, right? That is not only the Grover's algorithm for searching; you can use it for multiple applications. The choice is on you. Wherever you can map it, you can use it. And here is a wrap. Okay, I'll be sharing this with all of you. Yes, we stop sharing. So,
Thank you. Uh, question.
any question,
Uh,
anyone?
is, let me check if there is any.
I'm also looking for
Question
it.
might be there on the chat, but right now there is no question. I think.
Let me quickly go through it if I can find any question. No, there is no question that I can see on chat as well.
Question in the chat.
Thank you for your feedback. Yeah, it is very exhaustive, and to the
Uh,
maybe we covered only 10% of Grover. There is 90% more. The itself the like
yes, ma'am.
thesis of Grover you can check for the detailed ones.
Yes, ma'am. Thank
You
you so
cannot do any
much.
mix up.
Uh,
Yeah, I'm just answering. You cannot do any mix up between Grover and Shor. Shor is a quantum Fourier transformation, completely new paradigm, and this is amplitude amplification, completely new paradigm. And I don't know that whether there exists any such merging area or not. Till that there hasn't been, I guess. Okay, great. So exactly on time. Uh, you can think Grover in this way.